Right, good morning. I am going to do a few examples on McLaurin series, a couple of examples, and then an example on Taylor polynomial. I'll start doing the McLaurin series for f of x equals e to the power of 3x. This is exactly the Taylor series at a equals 0. It's the same thing as the Taylor series with centered at 0. So what we're going to do is we're going to take the function and plug a in, the derivative plug a in to compute the coefficients. So f of x is e to the power of 3x. This means that f at 0 is e to the power of 3 times 0. That's 1. F prime of x is 3 times e to the power of 3x. So we're going to put 0 in to get 3. F double prime of x is 3 squared e to the power of 3x. So if you put 0 in, you get 3 squared. If you continue, the nth derivative is 3 to the power of n times e to the power of 3x. It keeps adding a copy of 3 as a coefficient. So the nth derivative at a, in this case at 0, e 3 to the power of n times e to the 0. So what this means is C0 is 1, C1 is 3 over 1 factorial, C2 is 3 over 2 factorial, 3 squared over 2 factorial, C3 is 3 cubed over 3 factorial, and so forth. So Cn, the coefficient for the nth term, is 3 to the power of n over n factorial. So this is 1 over 0 factorial, which is 1. Okay. So our McLaurin series becomes, which converges to e to the power of x, e to the power of 3x, becomes 1 plus 3 over 1 factorial times x to the power of 1, x minus 0 to the power of 1, plus 3 squared over 2 factorial times x minus 0 squared, plus, which we can write it as, in this case we can write it as 1 plus 3 over 1 factorial x to first, plus 3 squared over 2 factorial x squared, plus 3 cubed over 3 factorial x cubed, plus, and so forth, which comes out as the sum of 3 to the power of n, x to the power of n over n factorial, n from 0 to infinity. So that's the McLaurin series for e to the power of 3x. Next example I want to do is McLaurin series for f of x equals sine x. So we're just going to do the same thing. Keep differentiating and then plugging in. In this case, f of 0, because it says McLaurin series, that's why I know a is 0. F of 0 is sine 0. The derivative is cosine x. So the derivative at 0 is cosine 0, which is 1. Second derivative is minus sine x. So second derivative is 0. The derivative of that is minus cos x. So the derivative at 0 is minus 1. The fourth derivative is minus sine x, no, minus of minus sine x. So the fourth derivative at 0 is 0. Now we're back to this spot. So the derivative would be this one, the next derivative would be that one, and so forth. So it looks like we're repeating these four numbers as 0, 1, 0, minus 1, and so forth. When the nth derivative n is even, we get 0. When n is odd, we get either 1 or minus 1. All right. So let's see, C0 is 0, C1 is 1 over 1 factorial, C2 is 0, C3 is minus 1 over 3 factorial, C4 is 0, C5 is 1 over 5 factorial, and so forth. So you can see that the even terms disappear, only the odd terms. So the Taylor series, which will converge to sine x, is now 0 plus 1 over 1 factorial times x minus 0 plus 0 plus minus 1 over 3 factorial x minus 0 squared cubed plus 0 plus 1 over 5 factorial x minus 0 to the fifth minus 1 over 7 factorial x minus 0 to the 7, and so forth, which is 1 over 1 factorial x to the first, 1 over 3 factorial x to the third, 1 over 5 factorial x to the fifth, minus 1 over 7 factorial x to the seventh, plus, and so forth. So these are odd numbers. So we're going to replace it, we're going to write them as 2k plus 1s. So I'm going to try to do either minus 1 to the power of k or k plus 1. I don't know. I will figure that out. Okay, minus 1. Every other one is negative. X to the power of 2k plus 1 over 2k plus 1 quantity factorial k from 0 to infinity. Now, when k is 0, 2k plus 1 is 1. 2k plus 1 is 1. When that means that the exponent is 1, we're looking at this term when k is 0. When k is 1, 2k plus 1 is 3, 2k plus 1 is 3. So we're looking at this term when k is 1. K is 2 and k is 3. Okay? Now, if you look at that, then k is 1. We want positive. This is positive for k equals, for k equals 0. For k equals 0, the exponent is 1, and we want positive. So it looks like minus 1 to the power of k will do it instead of minus 1 to the power of k plus 1, because when k is 0, we want it to be 1. This will give us minus 1. So that's just the McLaurin series for sine x. And if we compute the interval of convergence using the ratio test, we're going to get from minus infinity to infinity. By the way, this also has interval of convergence minus infinity to infinity. If you do the legwork and compute the radius of convergence and interval of convergence. Okay. The next example I want to do is Taylor polynomial for the function f of x equals cube root of x at a equals 8. Actually, we want to do third degree Taylor polynomial. Okay. Taylor polynomial for f of x equals cube root of x at a equals 8, and then we're going to use that to compute cube root of 9, okay, to approximate cube root of 9. So f of x is cube root of x, which is equal to x to the power of 1/3. We're going to differentiate that, so we'll write that down. So f of 8 is cube root of 8. This is 2. And we're going to save that. Take the derivative. The derivative is 1/3 x to the power of minus 2/3. I'm just using that to find the derivative. Okay? And if you simplify this, that gives you 1/3 times x to the power of 2/3. Okay, so stick a in, 8 in, so 8 to the power of 2/3. 8 to the 1/3 is 2. Squared is 4 times 3 is 12. F second derivative is minus 2/9 x to the power of minus 5/3. I'm just looking at this and doing the calculation in my head. I drop the exponent down to change this to minus 2/9, and then subtract 1 from the exponent. And if you simplify this, you get 2/9x to the power of 5/3. We're going to stick 8 in. That will give us 2/9 times 2 to the 5th. Okay, that's 2/9 times 32 comes out as minus 1/144. The third derivative is 10/27 x to the power of minus 8/3, and stick 2 in, so that gives us 2/27 x to the power of 8/3. So put 2 in, 8 in. This will give you 2/27 times why did I put the 2? It's 10. 10/27 times 2 to the 8. And if you cancel out the 2, we end up getting 5/3456. Okay, so because they say third degree Taylor polynomial, we will stop here. So the third degree Taylor polynomial is f of a, which is 2, plus 1/12 over 1 factorial, times x minus 8 to the 1, plus minus 1/144 times 2 factorial times x minus 8 squared, plus 5 over times 3 factorial x minus 8 to the 3rd power. That's the Taylor polynomial, third degree Taylor polynomial. I will simplify the numbers. 1 over 12 x minus 8. I'll multiply them out. 1 over 288 x minus 8 squared. 5 over, so this is a 6 times that number. It comes out as 27.36 x minus 8 to the power of 3. So that's the third degree Taylor polynomial. We don't want to FOIL it. We want to leave it like that. So that's the third degree Taylor polynomial for the given function centered at 8. Okay. One of the things students make mistakes on is they put 2 in here, cube root of 8. No, that's just simply 8. We're going to stick 8 in here. Okay, x minus 8. Okay. Now, let's use this to approximate cube root of 9, which is essentially f of 9. So we're going to approximate that by t3 of 9. So we'll use this to calculate cube root of 9 when we're supposed to use this to calculate cube root of 9. Okay, this is the exact function that we should stick 9 in to get the exact value, but we're going to approximate it by this function. So cube root of 9 is approximately equal to 2 plus 1 over 12 times 9 minus 8, 1 over 288 times 9 minus 8 squared, plus 5 over 20,736, 9 minus 8 cubed. This is 1, this is 1, this is 1, so it gives me 2 plus 1 over 12 minus 1, 288, plus 5 over. So that's the approximation to this. It comes out close to 2.0801 if you do put it in the calculator. Okay, so that is third degree Taylor polynomial and the use of it. So I just want to add one more comment, so that I would like you to memorize or at least recognize the McLaurin series for e to the x. This is x to the power of n over n factorial, n from 0 to infinity. Sine of x is n from 0 to infinity, x to the power of 2n plus 1 over 2n plus 1 quantity factorial minus 1 to the power of n. This is the one that we just computed a few minutes ago. And if you compute cosine of x the same way, what you're going to get is n from 0 to infinity minus 1 to the power of n, x to the power of 2n over the quantity 2n factorial. I keep writing 8 with radius of convergence of from minus infinity to infinity. These are three important McLaurin series that we at least should recognize. One way that I remember the exponents is that the sine function is an odd function. So all the terms, all the x's are of odd power. And the cosine function is an even function. All the terms, I mean all the coefficients of the powers of x are of even power. All right, I will see you in class tomorrow. Just check this video before you come to class. I'll review this a little bit in class also.